Hello, today I'm introducing the crash data analysis of HAT in a biomedical engineering perspective. Here's an introduction of the background. We place a dummy in a car and there is some accelerometer in the chest, head, and the pelvis. And all of that's gonna measure the acceleration of the dummy when the car is being crashed in the 3D dimension, which is X, Y, and Z axis. First, we graph the data into an acceleration over time graph, and we can see when time is 0, it is the instant time when car is being crashed. When time is 115.2, it is the time where the maximum resultant of HAT is there, around here, with the highest peak. So we assume the mass of the HAT is 5 kg, and due to Newton's second law, the maximum force related to the maximum resultant acceleration on the HAT in the direction of triaxial space, which is the same direction as the resultant acceleration, is F max equal A max times m. So 33.9.8, remember the unit is in Earth gravitational field, time meter per second squared times 5 kg. And that's gonna give us 1617 newtons. So here's some application on the analysis we got. The frontal impact has the most prominent injury, which is TBI, traumatic brain injury. The situation is the counter-coup brain injury. Due to Newton's first law, an object tends to stay at rest or moving at a constant speed due to the net external force, which is 0. So when we're stopped by a car in front of us, our head still tends to move forward as if it's still driving. So the head is gonna move forward while brain tends to leave backward. This causes the skull hits the brain tissue, and which can cause damaging brain tissue and neurons. The other situation is where an external force makes us move backward while our brain still leaves at the front, and that's gonna cause the damage to brain tissues again. So here you can see that can cause the crushed tissue, which is over here, and also the sheared tissues, which is really detrimental for our cognition. With really high speed in a car crash, it can cause a lot of problems like swelling, bruising, and damage to the brain tissue, especially like the parietal lobe, which can cause really bad things to the driver because it's gonna interrupt with the spatial interpretation. And that also includes the frontal lobe, which is the lack of focus and the language difficulties. The skull fracture is another situation where your skull is being forced by the car that hits you. So theoretically, 2,300 newtons is the force that can cause your skull to crash. And as calculated by the given data we got, the maximum force is 1617, which is sufficient to cause some serious partial fracture to the skull. Due to Newton's second law, the net external force equals the acceleration times the mass of the object. Thus, a larger mass and the net external force of the head can yield a larger force on the skull. And here's a graph that represents how common it is in the traffic that the TBI is happening. A solution to this is the airbag. It is really effective to reduce the force on the skull by reducing the time required to stop the car. And this is depicted as the impulse equation as the total impulse remains the same, the mass is the same, and the initial velocity is the same. But while we increase the change in time, then the force is gonna reduce. That's gonna help us to avoid some of the damaging tissue. So here is the simulation for the frontal impact. The whiplash is most prominent in rear impact, which is a really short time hyperextension and the cause of the tear ligament. At first, the vehicle is stuck from behind and our head tilts backward. Our torso rises up because our torso is attached to the seat and our head is not. Due to the law of inertia, our head tends to stay at its original position, which is relative backward to the torso. After initial impact, the head snaps forward again, and that causes the hyperflexion, and that's gonna worsen the tear of ligament. Here's a simulation, which is the resting hypertension, and then the head is gonna bounce forward and cause hyperflexion. The side impact has the most prominent injury in spinal cord, and that is caused by our head remains static while the force acts on the neck. The muscle and the ligament in the neck are stretched, and then the head moves backward to its original position in such a short time, which causes the fracture of vertebrae and compressed spinal cord segment, although it looks similar to the whiplash. Here's a simulation.